In this problem, we are having a circular naphthalene tube which is having an inside diameter of 2.5 centimeters and length of 300 centimeters, and air is flowing inside it with a bulk velocity 13 meter per second. The air is entering at 40 degrees Celsius and average pressure of surrounding is 1 atmospheric, that is 1.013 10 to the power 5 pascals. Now we can assume that the change in pressure is negligible, and we are also given with some important properties at 40 degrees Celsius only. For example, the diffusivity of naphthalene in air is 6.61 10 to the power minus 6 meters square per second. Vapor pressure of naphthalene is also given, that is 46.8 pascals. Kinematic viscosity of air is also given, 1.7 10 to the power minus 5 meters square per second. And there is an extra relation of fanning friction factor through this tube is given, that is 0.002534, Reynolds number to the power 0.11. And there are some also flat plate relations of laminar, turbulent, and transitional flow are given here for extra calculation. So the first part is the determination of average flux of naphthalene from the inner surface of the tube. So basically, we need to find out the flux through the inner surface of the tube when the air is flowing through it. So in second part, we have cut down that circular cylinder of the naphthalene into a flat plate. That means the length of the flat plate and the length of the cylinder are going to remain the same, and the breadth will be occupied by pi d, that is the circumference of that cylindrical tube. Now, the third part is like we need to maintain a mass transfer same as that of the case A in the B. So you need to find out how much length you need to have as a flat plate as compared to a cylindrical. So this is basically the schematic diagram of our problem, that air is coming at a speed of velocity of 13 meter per second inside a naphthalene tube. Okay, so this is a naphthalene tube. Diameter is 2.5 centimeter and overall length is 3 meter. And this everything is happening at 40 degrees Celsius temperature. Temperature is constant. So air is coming from this side and there is diffusion of the naphthalene into the air is there, and now from the another side the air plus naphthalene are passing from the another side. Now in this problem we are given with that the pressure is atmospheric pressure, that is 1.013 10 to the power 5 pascals or 1 atm. Delta P, this pressure drop across the length of the naphthalene tube is negligible, so we can neglect that. And we are given with the data at 40 degrees Celsius, the properties, some like chemical properties of naphthalene is there, like the diffusivity of naphthalene in air is given. Saturation pressure of the naphthalene ball is given at this temperature. The kinematic viscosity of air is given and meter square per second, and the fanning friction factor relation with the Reynolds number is given there. So now we will going to find out the transfer of moles of naphthalene in these conditions into the air. So moreover we need to find out the Na, that is in moles per meter square per second, that is molar flux of naphthalene into the air. Okay, so before starting the solution, first of all we need to check the Reynolds number of the problem. Okay, so first of all we need to find out the Reynolds number. So Reynolds number is equal to characteristic length, then characteristic velocity, then density upon viscosity. Okay, so this is a tube. So during the flow in the tube we need to take the characteristic length as the diameter of the tube. So in this case the diameter 2.5 centimeter will be the characteristic length. So now we are going to substitute all the values and we'll going to find out the answer. Okay, so now we have find out the Reynolds number. So this Reynolds number is in turbulent region because this quantity is greater than 2100. So now we have analyzed that the Reynolds number is in the turbulent region. So now we will going to apply the formula of the turbulent region of the mass transfer. So we can use the two equations. First is Linton-Sherwood correlation and another one is Sherwood-Gillen correlations. Okay, so depending upon the value of Schmitt's number, we need to check which relation we need to use. Okay, so now we're going to find out the value of Schmitt's number. So Schmitt's number is equal to kinematic viscosity upon mass transfer diffusivity. Now we're going to find out the value of Schmitt's number. So now we have find out the value of Schmitt's number, that is 2.5718, and now from here this is clear that we need to use the Linton-Sherwood correlation, because this quantity of Sherwood number is greater than 2.5 and it is nearly equal to 2.5. So we will use the Linton-Sherwood correlation for the better accuracy of our Sherwood number. So now we are going to find out the Sherwood number using the Linton-Sherwood correlation, that is Sherwood number equals to 0.023, Reynolds number to the power 0.83, and Schmitt's number to the power 1/3. Now we have Reynolds number, we have Schmitt's number, and now we're going to find out the Sherwood number to find out the heat, the mass transfer coefficient in the further calculation. So from Reynolds number calculation and Schmitt's number calculation, we got the Sherwood number using the Linton-Sherwood correlations. Now we need to find out the Kc, that is mass transfer coefficient, to find out our that is molar flux. Okay, that how much the naphthalene is diffusing into the air. Now the Sherwood number, as we know, the relation of Sherwood number and mass transfer coefficient is Kc into characteristic length divided by diffusivity, and this value is equal to 112.736. Now in this case, as we know, this is a like flow through a pipe, so characteristic length is equal to diameter of the pipe. So Kc multiplied diameter, that is 2.5 10 to the power minus 2, and the diffusivity is already given at this temperature, and Sherwood number we have already calculated. Now we will going to find out the value of Kc using the calculation. Now we are going to find out the value of Kc, and then we are going to find out the value of molar flux using Kc and concentration. Now we have calculated the value of Kc, that is mass transfer coefficient, which is an important parameter to calculate the molar flux. So now we have Kc, we need to find out concentration, that is concentration gradient between the air and the naphthalene concentration, to find out the molar flux. Okay, so now we are going to calculate the concentration gradient. So the formula of molar flux is equal to Kc, that is mass transfer coefficient, then the difference in the concentration, Ca2 minus Ca1. So this is the bulk concentration of naphthalene. So how much naphthalene is present in the bulk quantity in it, and this is the saturation concentration of the naphthalene into the air. That means how much naphthalene can go up, like the concentration of naphthalene maximum in the air at these conditions, at 40 degrees Celsius at 1 atmospheric pressure. So now, so at this condition we can assume that this Ca1 can be 0, because there is no naphthalene is present in air. So this is an assumption made by us to like refine our calculation and make them more simpler. So now in this case Ca1 is 0, and now we're going to find out Na. Now Kc into Ca2, and this Ca2 is the concentration, the bulk concentration of naphthalene in it. So this can be calculated based on the partial pressure of naphthalene. So the partial pressure is already given to us, and using ideal gas equation we can find out this bulk concentration of the naphthalene. So this Ca saturation, or we can write Ca2 equal to P saturation, that is the partial pressure of naphthalene into the air at the 40 degrees Celsius by gas constant into temperature, and this temperature is 40 degrees Celsius. Now by substituting all the values in the SI unit, this is in Pascal, and now gas constant 3.0 8.314 Pascal meter cube upon moles per second into this temperature is in Kelvin. So now we're going to calculate the value of saturation concentration into the bulk of the naphthalene. So we have calculated the concentration of the bulk of naphthalene and the answer is 0.01798 and the unit is moles per meter cube. Now we are going to find out the molar flux by simply putting the values of Kc that we have already calculated here, that is 0.02980 meter per second, and concentration we have already calculated. So just putting the values we can find out the answer. Now by just multiplying these both of the terms we can find out the answer, and the answer would be in moles per meter square per second. So the calculated value of molar flux is 5.35804 into 10 to the power minus 4, and the unit is moles per meter square per second. And we can also calculate the answer in kilomoles per second in 10 to the power minus 7. So this is the answer of the first part. Now in the same question we are having the second part, and which is also related to the first part, and it is goes something like that. We are having the naphthalene tube, and it is cutted axially, and when it is cut down and it is flatted, like this cylinder is just flatted in the shape of a flat plate. So in the shape of flat plate it is just turned into the flat plate, and now we will going to have a length that is equal to the height or the length of that cylinder, that is same is equal to 3 meters. Okay, and the breadth is equal to the diameter, that is 2.5 centimeters. So the main question is that now the same air, same temperature, same pressure is flowing through this flat plate at the same velocity, the 13 meter per second, at same temperature and pressure conditions. Now we need to find out that what is the molar flux or the molar transfer rate of naphthalene into the air. So now because we know that the contact area increases, and now we cannot use the relations of the cylindrical pipe or cylindrical correlations. So now we're going to solve this problem using Chilton-Colburn analogy and all the formulas of flat plate. So proceeding with that, first of all we would start with Reynolds number. So Reynolds number in this case will be the characteristic length multiplied by the characteristic velocity divided by the kinematic viscosity. So now because this is a problem of flat plate, so here the characteristic length will be the length of the flat plate, that is 3 meter, that is same as the length of the cylindrical case in the first part. So now we will just substitute the values. The 13 is the characteristic velocity that flows over the flat. So now we are going to calculate the Reynolds number using the characteristic length, that is the length of the flat plate, the velocity that is flowing over the flat plate, that is mainly responsible for the diffusion of naphthalene, and at last we are having the kinematic viscosity that is also given in the problem. Okay, so we get the Reynolds number as 22,94117.64, that is in transient region. Because this is greater than 5 into 10 to the power 5. So this is the criteria that shows that this flow is in transient region. Now we're going to take the relation of transient region of the flat plate. So now we're going to calculate the friction factor using that relation. So friction factor in the transient region for the flow over the flat plate will be now we are having this relation for the transient region flow. Now we're going to put the value of Reynolds number at both of these places, and we're going to find out the value of friction factor. So we're going to substitute the value of Reynolds number that is already given to calculated by us. Now we're going to calculate the value of F using the equation that we have calculated. So using this relation, we have find out the value of friction factor, that is 3.19488 10 to the power minus 3. Now we're going to use the Chilton-Coulomb analogy because this is a flow over a flat plate. Okay, and now we're going to use the Chilton-Coulomb analogy to find out the value of mass transfer coefficient. So using that relation, we have the relation for the mass transfer coefficient and the friction factor as this is the Stanton number for the mass transfer and to multiply by Scammage number to the power 2 by 3. Now we already have this friction factor, and the value of Scammage number we have already calculated, that is 2.5718. So we need to just put the value of Scammage number in that place, and now we're going to expand this term of the Stanton number in the mass transfer. So doing that, now we already know that we want this Kc, that is mass transfer coefficient, for this situation, and we know the characteristic velocity, that is the velocity that flows over the flat plate, that is already given in the problem, that is 13 meter per second, and we already calculated the F, we know the Scammage number, so we have to just calculate the Kc. So taking the terms at the right hand side, so now taking all the terms at right hand side, so Kc will be equal to F by 2 characteristic velocity 1 upon S Scammage number to the power 2 by 3. Now we already know all the things: characteristic velocity, the friction factor we have already find out in the previous part. This is the friction factor, and Scammage number we have already calculated in the previous part, that is 2.5718 to the power 2 by 3. So just calculating all these values, we get our answer of Kc, mass transfer coefficient, is 0.018062 meter per second. Now we have to just calculate the value for calculating the value of molar flux. We need to just multiply this Kc by concentration, saturation concentration, and we know that here it comes as a concentration gradient. So as we already explained, that is concentration, that is the bulk concentration of naphthalene into the air. So we have assumed that the concentration before the diffusion is 0 because there is no naphthalene present in the air. So this term is neglected or can be made 0. So we have already calculated the Ca, the saturation concentration, in the previous part, that is 0.01798 moles per meter cube. You have to just substitute the value because there's only change in Kc, there's no change in the concentration because the physical properties are same, only the flow pattern is different. So just substitute the value of Kc and Ca, and we will get our answer as 1.9890 10 to the power minus 4 moles per meter square per second. So this is the molar flux that we got, and we can also find out the answer in the kilomole. So that is the same answer but in 10 to the power minus 7 kilomole per meter per second. So this is the overall procedure or the solution of the second part, which is exactly same as the first part, but only difference is that in first part we are having like a circular cylinder kind of naphthalene, but in second part we have just made in the flat plate, and in that case we got the length as the 3 meter, that is the length of that cylindrical naphthalene, and the breadth is pi d, that is 2 pi r or pi d, that is the breadth of that flat plate, and all the analogy is as follows. So the third part is the continuation of the second part. So it is basically that we are having the flat plate in the second part. So now the question is that we get the molar flux in the second part as 1.98 something into 10 to the power minus 7 kilomoles per meter square per second. But in the first part we got the molar flux that is higher than the second one. So like in the first part we are having a cylindrical type of arrangement, and in the second part we are having a flat plate. So now in third part we need to calculate the length of this flat plate such that the flux is equal to the flux we calculated in the first part.
Okay, so because we know that the length is 3 meters, so we got the flux as 1.98 into 10 to the power minus 7. So for the flux of 5.35 into 10 to the power minus 7 kilomoles per meter square per second, what should be the length of the flat plate, so that we got this as an answer of our flux. So now proceeding this question, the only change we get is in the Kc, that is mass transfer coefficient, because the thing is that the saturation concentration is same in the case of part A and part B, it is same, but the only thing that changes the molar flux is the Kc. So the Kc in the first part is different and Kc in the another part is different. So to want the Na, that is the molar flux, as 5.35 10 to the power minus 7 in the second part, in the case of flat plate, we need to set the Kc of the circular tube is equal to Kc of the flat plate to get the desired the molar rate. Okay, so the Kc required will be 0.09807 meter per second. So this should be the Kc. So now the calculation is just reverse what we have done in the second part. Now we are going to find out the value of friction factor using the Chilton-Coulomb analogy, because we can apply that analogy here, because we are having the case of a flat plate, and for the flat plate we can apply the Chilton-Coulomb analogy here. So this is equal to friction factor, that is equal to Stanton number of mass transfer multiplied by Schmitt's number with the power 2 by 3. Now we need to find out the friction factor. So the Stanton number for the mass transfer is, that is Kc divided by characteristic velocity, and Schmitt's number we have already calculated. So we need F. So F will be now we have to just substitute all the values. The Kc is updated as this 0.029. So we have to just put the value of Kc here. Characteristic velocity you already know, that is 13 meter per second. There is no change in that. And the Schmitt's number we have already calculated in the first part. So we just substitute the value. And we need to write the answer. And the answer we get for the friction factor is nearly 8.6078 into 10 to the power minus 3. Now from here we don't know that this is the problem, that this could be the problem of the transient region flow, laminar flow or turbulent flow. So for that we need to first check by taking the assumption that that it is in the laminar flow or in the turbulent flow. So for taking the first assumption as turbulent flow condition. So for the flow over the flat plate and turbulent flow condition, we have the correlation of the friction factor, fanning friction factor, and the Reynolds number as 0.074, Reynolds number to the power minus 0.2. So this is the relation for Reynolds number greater than 10 to the power 8 for the turbulent flow. So now we will just put the value of friction factor that we have already calculated here in previous part. And we can find out the value of Reynolds number here. So we have calculated the value of Reynolds number using this relation, because we know the friction factor, and now we got the Reynolds number as this 46,956 point something. But we know we have taken the assumption as Reynolds number is in the region of turbulent region, that the Reynolds number should be greater than 10 to the power 8, but this is very less. This is in the region of laminar flow. So our assumption is completely wrong. So now we need to take the second assumption in the laminar flow, and continuously we need to take the third assumption in the transient flow. If the continuous assumption is wrong or getting wrong, so we need to take the third assumption. Okay, so for the laminar flow we are having the friction factor relationship 1.3828 Reynolds number to the power minus 0.5, and this is true for Reynolds number less than 510 to the power 5 for this one. Now we know the friction factor, we know we need to find out the Reynolds number. So Reynolds number will be so we could just substitute the value of Reynolds the friction factor that we have calculated here. And we're going to calculate the Reynolds number here. So now by substituting all the values, we get our answer as 23,801.93, and by taking an I-owner assumption, this value is obviously correct because this is less than 5 lakhs and 10 to the power minus 5. So our assumption is correct. That means we can say that this the flow is in the laminar region, and we can substitute the value of Reynolds number as 23,901, and the Reynolds number we already know, that is equal to the characteristic length multiplied by the characteristic velocity divided by the kinematic viscosity. And for the case of the flat plate, this is the length of the flat plate that we need to calculate. So by taking the values of the Reynolds number, we need to find out the L. The characteristic velocity is 13 meter per second, and the kinematic viscosity we need to substitute here, that is given is 1.7 10 to the power minus 5, and we need to just calculate the L here, and the answer is in meters that we get, and by just putting the values and the cross multiply, we can get our answer. So now we have calculated the value of L, that is 0.03112 meters. Now the thing is that in the first part we got the value of L as 3 meter, that we already has because we have flattened the cylindrical naphthalene tube. So it is in the 3 meter, and we get our answer as that flux what we get. And now the value of L is reduced drastically. It is 3 meter and this is 0.03. So why it is happening? The reason is that we are having the relation of friction factor and the length is that, using the Chilton-Colbert analogy, that Kc upon characteristic velocity, the scheme is number to the power 2 by 3, and now the relation is held by the laminar flow. So we can substitute 1.3 to it, Reynolds number to the power minus 0.5. Now this Reynolds number can be expanded as length characteristic velocity divided by kinematic viscosity, that is minus 0.5. Now we can substitute all the values and we can make in root, that is the kinematic viscosity upon characteristic length and characteristic velocity. Now from here we can see that this Kc is directly proportional to the 1 by root of characteristic length. So now we can see that when Kc increases from 0.01 to nearly 0.029, so then the value of L characteristic length decreases drastically. So this is the reason, because the characteristic length and Kc are having inverse relationship and in the root. So that is why by increasing the small value of Kc, we get a drastic decrease in the value of L. So this is all about the problem on the transport phenomena.